Good morning and good afternoon. Thank you so much for joining us for our September webinar. Today we will be doing a collaboration webinar with C-Therm. This will be our second collaboration. First off, we'll start with Marina Jajeh, who is our research associate with RheoSense. She holds her BS in chemistry from UC Santa Cruz. And then I also want to introduce C-Therm's host as well, Arya Hakimian, who is the application scientist at C-Therm. And without further ado, I'll go ahead and introduce Marina. Just a quick side note, we will be recording this webinar and all recordings will be sent through email after the webinar and once the recording is ready. You can also check us out on our social media pages as well as C-Therm through Facebook, Twitter, LinkedIn, and also our YouTube channels. Okay, and we'll go ahead and get started with Marina.
Hi everyone, good morning or afternoon, wherever you are. So for my portion of the webinar today, I will be discussing how dispensing, the viscosity is important for dispensing applications. And I will go into that. So dispensing, like a lot of other things, can now be automated, especially with the creation of like EV cars and things. A lot of those things have become automated. So with that, a lot of instruments and machines have now been created to help with that automation. And with that, a lot of these machines also need certain viscosity, certain materials with certain viscosities in order to operate properly. So just quickly, for dispensing, using a machine can help eliminate a lot of errors as opposed to someone just pouring your material onto whatever the area you're trying to cover with those materials. So using these types of machines can help eliminate a lot of human error. It could also help eliminate air gaps where some of these materials don't quite function as well if you have air gaps between the material and whatever you're placing it on. So it could help eliminate things like that. It could also help with just volumes of the materials you need. You know, by hand, it's kind of hard to gauge how much you're actually pouring or dispensing if you're using things like some sort of like dispensing gun, or you're just like dumping something into something else, as you can see in this image here on the side. So a lot of these machines could help eliminate those types of errors, and even just like overall positioning. They're quite accurate now, and they could very accurately dispense what kind of size you need, and the length, or how much you need to dispense onto the material. So depending on the type of dispensing method, the materials and the viscosity of those materials can change quite a lot. Also, another factor for the viscosity is the temperature of the environment you're in also affects the viscosity. So this is another factor. So if you're at colder temperatures, usually your materials most likely will have a higher viscosity. If it's a little warmer, it might be easier to dispense. So a lot of these things to take into consideration. While I was preparing for this webinar, I actually saw that there are quite a few machines that actually account for these temperatures changes, because a lot of these dispensing things take places in like a plant where the temperature might not be regulated. And if it's similar to plants I've worked in the past, it's usually very cold in the morning, and then as the sun comes out, it increases in temperature throughout the day. So this definitely can affect your materials. But it looks like they do have some types of machines that can help regulate those temperatures. So that might not be as much of a factor, but it's definitely something to consider with your materials and your dispensing of these materials. So some of the common dispensing techniques that I came across were bonding, sealing, and potting. So bonding, which I have an image of here, of this nice red material being dispensed. Bonding is an adhesive that is used to join two parts together. This is a very useful technique for certain materials that you're trying to bond together, because it does this without having heat or changing of the material at all. So this is very nice, where you could just easily put this adhesive, place your two things together, and both surfaces are still like intact and they're just as nice as before the bonding took place. Another common one is sealing, which I have an image of here. And this is kind of similar to bonding, but you're creating more of a seal. And this is more of a barrier to protect the components from outside influences, such as like temperature, moisture, etc., things like that. And as you can see here, this is being dispensed into a line right here to help create that bond, seal that we need. Another common dispensing method is called potting. Potting, from what I found, looks like it needs the lowest viscosity fluid to do this sort of dispensing technique. And basically what you're doing with this, as you can see in this image here, is you're taking a low viscous material and you're basically dumping it over components. And this is to protect components inside of something. And this is to protect them also from dust and other environmental influences. Another very common thing that gets dispensed excuse me, nowadays is thermal conductive paste, which is this image right here. And as you can see, these are very high viscosity materials. I was able to test one and I have some data to present to you for that. And the one I tested, I think the highest I got at lower shear rates was around 60,000 centipoise, which is very high compared to maybe something like this, which is like a few thousand, maybe a few hundred. And for the thermal conductive paste, these ones have very special equipment, especially depending on if it's one component thermal conductive paste or two component. And these machines are equipped to handle those high viscosity materials as well as even help them cure. But these thermal conductive compounds are very useful for electronics as well because they help to dissipate heat in a very tiny area. As electronics are getting smaller and smaller and the space to put them in is getting smaller and smaller, heat transfer can be a big issue because I'm sure as you're all aware, like when you use your cell phone, right, like the longer you use it, it gets hot, and that heat just kind of gets transferred into like the environment. But if it's something inside like the actual phone or some other thing with electronics, it needs another way to get rid of that heat effectively so you don't burn out the electronics or damage anything internally. So this thermal joint compound can help eliminate that. And the instruments, the machines they use for these can also, if they're properly picked for the type of material you're using, they could dispense these without creating air gaps, because air gaps, especially in this application, could not have an effective heat transfer and could cause damage. These are just all things to consider for that. So very briefly, before I go over some data that I collected, I was provided some samples from C-Therm, one of them being the thermal joint compound. Another one, or another two were liquid rubber, part A and part B. I did not mix them together and run them through our technology. I ran each component separately, as these things do tend to cure and our instruments aren't really made for more solid materials. And I also got another few samples with aluminum particles. So I'll be presenting the data for that after I briefly go over our technology. So our technology uses a viscometer rheometer on a chip, or VROC for short. All our instruments that we have here have this very same core technology. Inside the chip, we call it in-house, it has this rectangular flow path. This flow path is well defined, so we know the dimensions of this flow path, excuse me. We also, in the flow path, to measure the viscosity, we have these pressure sensors, and this is to measure the pressure drop, because viscosity is the resistance to flow. So by measuring this pressure drop, we can get some sort of relationships where we could help get the viscosity. Also in our flow channel, you can see we have this like laminar flow here, which is the shear rate, and as the shear rate goes across, it get a pressure drop on the sensors, and then this drop with some other relationships that we have here, we could help measure the viscosity of that. Let's see. Yes, as we measure the linear pressure drop along the sensors, we have a fixed flow rate, which we control externally, and this allows us to have a very constant and consistent flow throughout our flow channel. And from the flow rate and the fixed defined channel dimensions, we can calculate the shear rate. And from the slope of the pressure drop and the channel dimensions, we can calculate the stress. And if we take the values of the shear rate and the shear stress, we get viscosity defined over here. All right, so after that, I'm going to briefly go over the data that I collected. So here I have the liquid rubber components, excuse me, the part A and part B. I also will say I tested all of these at room temperature. And as you can see, the components separately are Newtonian, which means their viscosity does not depend on the shear rate, or it's independent for the measurement you get. And as you can see, one part is slightly lower than the other. So this information is useful for when you're dispensing these, because usually you would dispense both of these together into something. So this information is good to know, where it's like, oh, maybe we need something that could dispense this for us, instead of someone coming over and pouring it in, as this one is quite high. It's over 5,000 centipoise here. Let's see. So for the next component I got, this was liquid rubber part B with alumina particles at room temperature. Adding certain things to your materials can also affect the viscosity. It can lower it or it could higher it. As you can see here, we had two different concentrations of alumina particles. And as you can see, they both lowered the viscosity of the part B. If I go back quickly, we can see here that our part B is this one at the bottom, and it's around 15 to 1600 centipoise. And by adding the particles, you can see it lowered the viscosity quite a bit. As depending on the concentration as well, it will lower it even more. So this would also could help if you have like a specific thing you need to dispense, and maybe it's slightly difficult, or you need to add something for your formulation for your dispensing of these materials. Measuring your viscosity could help see if after adding these things, if your material is still, excuse me, could still be dispensed properly or evenly, or for your application if you need that. Right, and here we have the thermal joint compound. This was also tested at room temperature. And as you can see, this material behaved slightly differently than the other part A and part B for the liquid rubber that I tested. This one had some shear thinning properties, which means depending on what shear rate you run it at, the viscosity will be different. And as you can see here, at these lower shear rates, I got about 60,000 centipoise, and as I increased my shear rate over time, it dropped less and less. Still quite high compared to the other materials that I tested. But you know, this could also help if maybe you do need to do a hand dispense, like someone needs to come and dispense this for you. It might be easier to dispense, but then it's also nice because after you dispense it, it'll go back to its higher viscosity state. And this is also nice for the joint compounds because usually these compounds need to stay in place once they're dispensed. So this is just also nice to see that you're at lower or at not moving at all, your compound will stay in place when you put it after you dispense it. All right, and that concludes my portion of the webinar. I'm going to very quickly hand it over to Arya, and he will continue with the rest. Okay, Arya, I think you should be good.
Perfect. Thank you very much, Marina. Okay. So yeah, just let me get these slides up on screen here. I believe if I could get a confirmation that's working good for everyone.
Yes, it looks like we can see it.
Awesome. Perfect. So yeah, hey everyone. My name is Arya Hakimian. I'm an application scientist from C-Therm Technologies. And today I'll be kind of continuing on a little bit of what was discussed here, taking a look at processability and some thermal considerations for materials used in the EV space. Oh, there we go. So when we're looking really at these materials, I'll be going into that really under the guise of thermal conductivity. And really that's what we at C-Therm focus on. Really our purpose statement is simplifying thermal conductivity testing for the materials of tomorrow. And if you're in this space actively, you'll know that, you know, really thermal management, thermal interface materials that are being incorporated into these advanced electronics and EVs are really what are at the forefront of development today. So from C-Therm, we do this through the advancement of transient-based methods for thermal conductivity. Primarily the instrument that I'm showing here is the Trident platform. Trident was developed as a modular system, giving you the option to pick the method that is best suited for the task at hand. You can see there are 3 different sensor types laid out in front. Each one of these, of course, has application to a specific type of material, different testing environments, different conditions, sample sizes, etc. For the purposes of our session here today, I'll be primarily focusing in on this sensor right here, which is the MTPS, or Modified Transient Plane Source. As well as providing some details on its operation, some application examples, and some data collection. I will just briefly mention these, although they won't be a focus of topic here today, just for your knowledge base if this is new to you. This one in the middle here, this is a transient line source, or TLS. As you can see, it's a needle probe style sensor. This is a great option if you are dealing with samples that are more chemically aggressive, sticky, tacky. Frankly, some adhesive type samples are really good to test with this type of sensor. And then lastly, on the far left here, this is the more traditional transient plane source, or TPS for short. The TPS has some crossover in application with respect to solid materials that the MTPS has as well, although, as you can see, quite different in its sensor design as well as its approach to testing. But that being said, we'll keep going here. And again, coming back to really the main topic of today's session is looking at really the material development considerations. There are, of course, a wide range of properties that need to be taken into account when developing materials, you know, coming from either the structure that you're working with, thermal performance in this space, as well as the ability to process those samples. And really taking a holistic approach to the development is, of course, going to be the best way to make sure that everything is working as intended. But for my session here today, I'm really going to be diving in on the thermal conductivity side of things. So the reason for thermal conductivity being one of the more important aspects to material design is related to the fact that it is at its core the property that's going to manage heat dissipation. If you look at where your different electronics are going to fail out at, this was a quote taken from a conference 2017 there. You know, there are multiple factors, different environmental factors that can happen when we're talking about where things are going to break down, but noting that the temperature considerations account for almost half of the faults. Mechanical considerations through vibrations, humidity, different environmental considerations, of course, can be at play, but temperature is amongst one of the largest components. And when we're talking about breakdown from temperature, this really, is tied in very directly to thermal runaway. This is something that, you of course want to avoid at all costs, especially if it is going to be in a product or a system that is being used by a person. You see the news cycles where things catch on fire, whether that's the car, the cell phone, what have you. This primarily occurs through this mechanism, and thermal runaway is essentially a form of a positive feedback loop where you're generating heat within a system. This is resulting in an exothermic reaction, further increasing that heat, increasing the rate, and so on and so forth. And if you don't have a mechanism for the heat to escape from the system and essentially slow down this reaction, that's where these destructive events can come from. Now, mitigation of thermal runaway is accomplished through a thermal management system. These can take many different forms here, but core to any thermal management system is the thermal interface material employed. The thermal interface or material, or the TIM that's involved, plays a very significant role, because if you have heat traveling from your component, your electric or your heating component, to that thermal management system, which is, it could be an active, hybrid, or passive system, pulling that heat away, there's going to be this joint that occurs. And of course, these two materials in contact are not perfect. These microscopic air voids, or these gaps, are what's going to really impede heat transfer through the system. And where the thermal interface material comes in, it bridges that gap and assists in that heat transfer. And these can take various forms. These can be greases, potting compounds, adhesives, PCMs, as was mentioned at the beginning of the session today. And of course, each one of these act primarily to remove, or I should say, transfer heat between these components. But in all cases, again, really thermal conductivity is a key indicator of material performance, as it will really dictate how efficient that heat transfer can happen. Specifically, continuing with thermal adhesives here, thermal adhesives are, of course, a form of a TIM, but they also provide a means of bonding components. So again, from more of a structural consideration, so kind of in the first slide that Marina presented with the dispensing, these can be used to stick pieces together or seal them in place. Usually taking the form of a 2-part or 2K resin. Some thermal adhesives are also in the form of a tape as well. But what are the main challenges with any of these materials is the base chemistries. They're polymer in nature, and they typically have low thermal conductivity. So just inherently, the base sample that you're working with isn't a great medium for transferring heat, especially if you can compare the thermal conductivity of just a standard polymer to something like a ceramic or a metal, which are of course in the hundreds of watts per meter Kelvin range. So there has to be a way to improve on this. And I would say, without a doubt, one of the most common ways of doing so is introducing filler into your sample. Fillers are really what are going to do the heavy lifting with respect to heat transfer. So whether you're developing samples by just simply adding more filler, generally speaking, a higher filler load should result in a higher net thermal conductivity, better heat dissipation. With a certain caveat there, I have an example to kind of highlight where this may not always be the case. The aspect ratio of the filler, so really looking at not only the amount, but the shape, the size, and the form of the filler that's used. Even if it's all the same base material, this can have a net impact on the overall performance that is observed. And also the filler organization and distribution, and this will be one that I'll touch on as well. Generally speaking, if the system that you're generating is well organized, has better pathways for heat transfer, that will also result in a net increase to that performance. So there's a few different areas here, but of course all under the guise of the fillers really doing all of that work. Now there's plethora of example studies out there. We've, some I just put on screen here. These are all using our MTPS technology, just some example studies there. Plenty of additional resources available at the C-Therm website. Definitely feel free to check those out. I pulled a few that I'll just briefly share some of the highlights with here going forward. This was from a group in a few years back, looking at a graphene nanoparticle filled system. As you can see, very, very plainly in kind of the data here, increasing that volume of the graphene nanoparticle did result in a net increase to performance. Again, this was all tested for thermal conductivity, as you can see, again, using the MTPS. Similarly, here we look at another filled system. This was a PCM-based system, again, from a few years ago. But again, kind of clear trend here as you introduce different fillers, different additives into the system. And in this case, they actually looked at multiple additives in a more of a synergistic manner. We see a net increase in performance as well. And again, this was all done using the MTPS. So I do want to just do a brief run through of the method for those that may be interested. This won't be a super in-depth run through. If you did have additional questions, definitely feel free to ask. But at a high level, a few things to take note of. It is a single-sided sensor design. You can see kind of a diagram of the sensor here. Provides values for both thermal conductivity as well as thermal effusivity. So there are two main properties reported from the sensor. Very fast measurement times. Being a transient technique, it will have amongst one of the faster testing times, especially if you compare that to more traditional steady state options. The MTPS will always be significantly faster and transient in general as well. With the MTPS, there is a proprietary guard ring technology that is incorporated to the sensor. This is a very important aspect to the design of the sensors. It has an influence on the directionality of the measurement, which I'll speak to in a few minutes. But then lastly, it's very versatile, especially if you are in this space developing materials, whether it's for thermal management or really any other industry. Testing solid, testing liquids, testing the powders, maybe those filler samples individually or pastes. It's very flexible in that regard. So it does give you quite a wide range of testing capabilities. Of course, covers a lot, but not everything. And that's exactly why on the Trident platform, again, there are those other methods that can also come into play depending on the situation. So from a principles of operation standpoint, again, not going to go too deep into it here today, but high level here, the sensor coil on the top side of the chip there, it heats up to deliver a pulse of thermal energy for our measurement. The system is simultaneously monitoring the change in temperature that occurs as a function of time. And as you can see, different materials, we have an example of a foam and a metal, which are really at two opposite ends of that thermal conductivity kind of range. They'll respond quite differently to that temperature rise. So the foam, you'll see a much steeper rise in temperature, whereas a metal will be much flatter. But essentially it's based on the rate of change that's observed over the measurement duration, which is what's used to determine the thermal properties of the sample. And the nice thing with the MTPS is this is all done automatically within the software. The MTPS is a calibrated technique. Within the software package, there are a range of options that you can pick from. So again, whether you're testing something more insulative in nature or something more conductive, there are different options that you can select. So of course, I'll close it out there, but if there were any additional questions, happy to discuss that later on. All right, so I wanted to go into a few case examples, kind of how the sensor can be used in testing some of these materials. The first one here will be looking at thermal mapping of a sample in a cured state. So this is, not necessarily looking at the processing of the sample, when it's in its uncured, kind of that resin form. We're now looking at it in its final state there. But one of the things that's really important to many groups is quantifying the distribution of the filler within that cured sample. Again, you can add a lot of filler to a sample trying to boost that performance, but if it's not distributing or dispersing evenly within the sample and curing in an even manner, this can result in some significant issues. In this example we're showing here is a very visibly obvious example, but it really helps to highlight the point here. This was an epoxy resin filled with a conductive metal nanoparticle, and as we can see, very non-uniform. With the MTPS, because it's a single-sided method and it has that controlled directionality with the guard ring, we can place the sensor at different discrete locations and get a localized measurement for thermal conductivity. And then, as you can see in this picture here, kind of overlaying that on top of the sample, which can then be used to correlate back to if that material is being dispersed evenly or not. Obviously, in this example, we could just look at it and tell that based on a visual inspection alone. However, there are many materials which are, of course, opaque in nature, or you're simply not able to do that type of visual detection as easily. But really here, just to kind of show how it correlates well, the top right here has one that came in at one of the highest effective measurements. And as you can see, spot number 3, where that was tested, very densely populated with that conductive filler. Compare that to, let's say, the top left, which was amongst one of the lowest measurements, and again, tested at a location where, quite sparse with that filler present. So again, just gives you the ability to do this type of assessment, quite rapidly as well. So if you're dealing with high sample throughput, whether that's in the R&D stages or even later on in QA/QC applications, this is kind of a few ways that the sensor has been employed by some of the groups that we work with. And this is actually just a paper that was published, it was actually this year out of China, where they used the MTPS to investigate filled systems. And it kind of just continues on the point that I was just touching on with respect to the distribution of the filler inside of the material here. So of course, they were looking to improve the thermal performance of these hydrogels using graphene. But the data set that I'm showing here, we can see that the thermal conductivity results in the second graph, even though they're introducing more, increasing the graphene dosage, at a certain point it started to decrease, which is counterintuitive to what you might expect. But what they had noticed is that at a certain point, based on the filler load, the mechanisms that were involved in the curing and kind of the mixing and the production of these samples, once they exceeded a certain limit, the distribution that occurred at the higher loadings were not as uniform. They got more of these cluster clumping samples, and thus they actually saw a net decrease in thermal conductivity. So this is just one, again, kind of secondary example there where a higher filler loading does not necessarily equate to better thermal conductivity performance. So really, again, determining not only how much filler you're adding, but how well it's mixing and curing in that product can be really important to the end quality of the material that you're working with. But I'll pivot now just into taking a look at some of the feedstock materials, really the uncured resin, because again, of course, the end state is going to be very important, but there's a lot of things going on in that, really in the dispensing, as was mentioned earlier, and really also taking a look at how the thermal conductivity of those materials can play a role, but also how you can use thermal conductivity to monitor some of these issues that might be at play. So if you're dealing with a really small portable electronic, you may only be using a few milligrams or a few hundred milligrams of sample to kind of get that done. But many of the groups that we've been working with in the past years, when they're developing EV battery packs or dispensing into these larger systems, they're using massive amounts of material. Generally, they're 55-gallon drums, part A, part B being introduced into these automated dispensing systems. And this is really where the optimization process becomes really important with respect to multiple material parameters. One of the ones that we're focusing on is really the stability issues that can occur in feedstock sampling. Sedimentation is, I'd say, one of the bigger issues that can be at play, which is essentially where instead of having an ideal suspension, over time, eventually those fillers will start to settle towards the bottom side. You can also get agglomeration that happens within the sample if they're not stable in that storage state as well. And the reason this is troubling or an issue for many of these larger groups is that imagine if you have a barrel that you assume to be evenly dispersed with that filler, but it's sedimented towards the bottom. If you're pulling, most of these dispensing systems pull from the top of the barrel and move down. So if you're dealing with a system that has the sedimentation going on, a lot of the material, or I should say pretty much all of the material that you're taking in that first 75% here is going to be void of filler, or void of a significant amount of filler, meaning that the net thermal properties that you're expecting as they're being introduced in that battery pack or that electronic system is not going to be hitting the thresholds that you're expecting. And of course, this is where those heat dissipation issues can come up. You may end up scrapping a specific line or kind of a bunch of batteries that have been produced, and that can be quite costly. So looking at ways of monitoring this before you get to that end stage is something that we've been working with some groups by integrating the sensor in for more of a process monitoring side of things. Again, using the same MTPS by placing it in these barrels in these different dispensing systems, this is something that we've been able to assist with, kind of giving you that knowledge before it gets to this called an unfortunate state. But I have a kind of a mini case study that shows this more on a kind of a benchtop scale application. And of course, this was done through the monitoring of the thermal conductivity of the sample. You could also look at this in terms of thermal effusivity as well. But the idea here is our setup. We took various weight percentages of alumina and incorporated it into a liquid silicone resin. These samples were essentially prepared and mixed and placed in these large columns you can see here over top of an MTPS sensor. And we took measurements over quite a long time period. It was a couple days, and monitored the change that occurred as a function of time. This is kind of a visualization of that alumina powder that had settled towards the bottom of the of those tubes overnight. So again, this sample here wouldn't necessarily be pure, I'd say exactly representative of these larger feedstock materials, because there are stability agents that are introduced, thixotropic agents as well, that help with some of that stabilization. But again, really you're fighting time, and at a certain point, these sedimentation agglomeration issues will effectively take over. But what we can see here, just some measurement data, thermal conductivity graphed over a few data points here. So this up to this point is about 9 hours. So we did it for about a day. You can see that the 0% weight alumina, of course, didn't change because it was just, of course, just the pure silicone resin. So essentially unchanging the entire time. As we introduce 0.5% weight of alumina, we see a certain trend line and then kind of teetering out. Baselining at a kind of a certain value here. Of course, this is where most of that filler had settled towards the bottom and is in contact with the sensor. But then what you'll see is when we add different weight percentages, not only do that end value change of how much is kind of settling towards the bottom as more is being kind of picked up by the sensor, the curve and the curvature of the line also changes. So this can have some bearing. I believe there was one more, yeah, and the highest weight loading, again, kind of a different form as well. And again, there's different aspects at play here, but the kind of what was being mentioned at the beginning, the viscosity of the sample plays a significant role in how this plays out. The stabilizing agents, the fillers that are incorporated as well, these could all have a net impact on the behavior of these systems. And it's something that, of course, needs to be taken into account through the development, especially as these systems are continually changing. Formulations are kind of changing and advancing to hit new thresholds, new targets to help accommodate the temperature limits that some of these groups are trying to hit with their vehicles or their devices. So in conclusion here, just got a couple of final slides I'll wrap up on. Thermal interface material performance is, again, highly influenced by the fillers. The fillers are going to be I would say, #1 consideration with respect to that thermal performance. However, again, by just simply adding more filler, you can encounter some issues. And then, of course, looking at that from more of a holistic approach as to the other properties and how that's impacting performance as well. Of course, testing the end product is critical, and this is actually, the end product is of course what most groups will baseline their technical data sheets and all their product certification information on. But again, monitoring the uncured material performance can provide some insight into how it's behaving, and again, using it as a QA or QC or like a monitoring tool to help reduce waste that can potentially occur downline. And of course, as highlighted here today, the MTPS is a method that can really be used to test both the pre and post-cured samples. Again, whether you're in the R&D setting, benchtop application, or more interested in maybe some inline, there's definitely some capabilities there that we could help with. So, thank you for joining here today. My contact information here is on screen. If you did have any questions that you would rather reach out one-on-one, our kind of core team is also available to discuss if this was something you're perhaps interested in bringing in-house. Also give us a follow on LinkedIn. That's going to be where we post all of our, I'd say, most recent up-to-date information, new blogs coming out, different application notes, papers, and webinars, and so forth. And just speaking of upcoming events, upcoming webinars, one thing I wanted to leave you all with, if this was interesting and maybe you want to learn more or kind of talk about a different topic with respect to thermal conductivity, we will be at 2 shows in the US this month, October 3rd to 4th at the Advanced Materials Show in the US. I believe this is in Columbus, Ohio, as well as midway through the month, October 16th to 19th in Cleveland. But if maybe the in-person isn't as appealing for you, we are also hosting quite a few webinars this month on a range of different topics. We have one coming up October 4th, looking at thermal conductivity of self-adhesive tapes. We have a textiles focused webinar coming up October 20th. And then at the very end of the month, a phase change material focused webinar as well. And with that, I will end my section. Again, thank you everyone for joining.
Thank you, Arya. That was very informative. I also learned a lot from that. We're gonna have a little time for some Q&A. We already have one question on the screen here. Someone asks if a copy of the presentation materials will be available. We normally don't have the slides out, but we will have the webinar on our channel, the Viscosity channel on YouTube. Feel free to check it out. We will also distribute the webinar to anyone who signed up, so you will get a copy of this recording as well. I'm gonna wait a few more minutes to see if any other questions pop in. Oh, it looks like we have another question. Let's see. I believe this one might be more for Arya. Have you done any work on sedimentation rate over time for filler feedstock?
Filler feed. So maybe just to clarify, looking at how a filler inherently settles in just kind of how it, like the filler itself is being stored, or if it's integrated into a kind of a polymer system. So if it's, I guess in one case, I guess both, we've looked at larger scales, mixing and blending of powders, different types of filler materials. That's more from a processing side of things, but our sensors have been integrated into some of these kind of like industrial tumblers, let's say, that can be used. But if it's more under the guise of looking at the sedimentation in a filled system, then yes, especially if it is in a dispensing apparatus, being how it's integrated into some of these systems, that is in kind of, I'd say, more of an inline application. It wouldn't be as kind of set up with the benchtop, but it would be a similar technology employed. As far as materials settling in more of a smaller scale, there's a few different groups we've worked with. I believe we have some testimonials on our website, so you can check out some of the names there. I don't want to give away any information I shouldn't, but many groups that are looking to formulate the materials, so taking these kind of the base resins and then adding fillers, different amounts, different types, and kind of letting those cure, monitoring that curing process. That is something that I know some groups have done with our system. I've collaborated with a few groups on some projects in that vein. But yeah, it kind of depends exactly on the specifics there, but generally speaking, especially with the MTPS, it is really geared well towards those types of applications. So depending on the environment that you're in, kind of the chemical compatibility, the things of that nature, there's definitely some potential for that, if that's of interest to you.
We have some more questions coming in. This next one says, MTPS can be used to measure fillers on their own, correct? How much material in powder form do you need to be able to measure the neat filler?
Okay, yeah. So the sensor itself, you kind of saw in the pictures, it's basically a flat surface. The active area, that circular disc, it's about 18 millimeters in diameter. Call it 2 centimeters. We do have what's called a liquids and powder cell. It's basically a little metal fitting that goes over top, and then you could just fill that up with whether it's a liquid, a powder, paste, what have you there. It holds upwards of about 3 milliliters of total volume. So depending on the size of the filler that you're working with, it'd be about that much. One of the things just to keep in mind is that if you are measuring a powder or a filler, just a neat material by itself, one of the things that can come up, especially if it's loose and it's not compacted down, the interstitial air that's going to be present within that medium will have a large impact on the performance. Generally speaking, you can see orders of magnitude or multiple orders of magnitude lower than kind of the pure solid. So for example, if you took like a piece of copper and tested it, it's in the hundreds, 400. If you tested that in a powder form, it can be significantly lower. But that being said, you do have the capability to test the neat filler. That's definitely doable. Many of the groups, though, would opt to test it as it's inside of the matrix that you're looking to use. That can sometimes give some more, I'd say, representative data, but in either case, I do know we have setups available for both.
All right, looks like another question we have here. It says, I know it depends on the material, but your last alumina loading study, what is the thermal conductivity of the base component you are transferring heat from? Or was the 0.157 the rate of that or the unloaded material?
Yeah, so the base, that kind of flat line at the bottom would have been representative of just the silicone resin. So anything above that was related to kind of how much filler was settling down onto the sensor. And I guess different, the more you added, we saw that final value kind of creeping up higher. So, as you can imagine, probably densifying more over that active area, the more filler that is settling over the suspension there.
All right, so I think this question is for me. The RheoSense thermal joint compound room T-graph showed data scatter at shear rates above 500. Why is that? There could be a few different reasons why. A lot of this could be material based. Sometimes when you add shear is a form of deformation and it could cause some things to just come out of sample. So it's very possible that, or either when I loaded it, there might have potentially been some small bubbles. It's hard to tell with the paste when you're loading it into the syringe. And I, of course, tried my best to make sure no bubbles were present, but it's very likely there were pockets of it. And it's possible that these just became present as the sample went through the syringe, and maybe there were just different little areas with these pockets of bubbles, or it was possible that there was some sort of material instability or separation or something that happened at those rates. A lot of those are sample dependent, and it will just vary from compound to compound. Let's see, we have a few more. What determines whether feedstock settles or agglomerates? And this is kind of related. What forces are in play that drives toward agglomeration?
So I would say I'll try to answer that to the best of my, again, from like a thermal side, I could probably provide some more insight as to the kind of the chemistries involved in kind of how that filler and the system will interact. It might not be my, say, my strong suit, but generally speaking, it has to do with the stability of the system. And that is often, in the example that I showed, it was just a filler added into a resin. So, as we would expect, we saw that, settling or kind of, settling towards the bottom quite quickly. In these more optimized systems, and I believe we actually, on our website, we have some application notes, and actually a past webinar we did with a group that really focuses on that. That's kind of called their bread and butter. They develop these materials. We did a test and we showed that the stability of the system was in fact quite good. We sampled from the top, middle, and bottom of a drum and tested to see if there was any settling, and there wasn't. And the way they talked about that is, of course, it has to do with, really optimizing the loading conditions of the filler in the resin, the base properties of the resin itself, but then also adding in those stabilizing agents. And one of the really important aspects is the thixotropic properties of a material, because that has to do with how it's going to change, whether it's just sitting at rest. It should be quite, I believe one of the things it does is keeps it quite viscous, so it stops, or it helps to reduce that effect. But then when you apply a force to it and it begins to flow, like being applied in a dispensing system, those properties change. So again, it really depends on the chemistries involved, but as far as picking up on that and testing it, that's definitely something that we have some experience with. But exactly what's causing the issues, or the biggest issues, let's say, it can vary quite significantly.
All right, looks like we have a few more questions. Let's see. I'm just reading over these very quickly to make sure no new ones have reappeared. Okay. Let's see. Can the dispensing process cause sedimentation or agglomeration?
So I would say some of the dispensing groups that we've worked with, they again, I have a kind of a high level understanding of the systems that are involved, but there's almost a basically it's removing sample from the top of the barrel, so it's moving down and taking sample up and pouring it into, generally it's in a mixing head, and then it'll come into one nozzle and then dispense that two-part mixture and let it cure as it's moving along. As far as the impact as it's occurring, it would most likely be related to this, like the age of the system, or the age of the barrel, how it was stored, different environmental factors like this. I know one of the big issues is, and a lot of people initially might think, well, if I have a material that's, it's settling or it's agglomerate, why can't I just, if you start mixing it up, then you can get it redistributed better and, maybe back to its original state. But in a lot of these samples, because they're so thick, if you agitate or mix it, you're going to incorporate air bubbles into those systems. And having air in air inside of a dispensed line is going to be almost worse than just the base resin without filler, because air is extremely insulative. Air comes out at about 22 milliwatts per meter Kelvin, which is, you know, significantly, that's an order of magnitude lower than most just base polymer systems. So maybe hard to say there. That might be something that I guess might be more get some more information from one of the dispensing groups themselves. But I can say that the bigger issue would be that if you were to manually introduce some type of mixing to the system, that can almost make things worse than they were at the beginning.
All right, and it looks like there's one more question here. Can viscosity be used to monitor agglomeration? Oh, and this is also slightly related. Can viscosity be used to monitor stability and homogeneity over time? I imagine with these types of materials, yes. There are some other materials where as they separate, or you do get some sort of things that, you know, like there's just some sort of separation. There is a change in viscosity. In order to do that, you would first need to know what your viscosity is, what it is ideally mixed, and get some measurements from that. And then as you test it over time, you would see if this changes at all or drastically, and even visibly, if you can see your sample over time. Sometimes you can't always visibly see it, but sometimes, you know, as you, a lot of our instruments use a syringe to load our sample. So a lot of the times visually, if you look at the syringe over time, you might be able to see some sort of separation or, you know, some difference in visually what the sample looks like. This could indicate some sort of separation or the agglomeration or lack of that homogeneity that was once present. If it's not visibly, you're able to see that. Sometimes in the measurements you will see maybe your transient curves for your viscosity will look odd. Maybe if you run at the same shear rate over and over again, maybe, for example, you run it at your after you just mix it and it's like 100 centipoise, and you come back and then maybe it's like 50 or like 90 centipoise, for example. So it can be used to monitor this over time as things separate. All right, we are at 12 noon here Pacific time. I'm gonna just double check, see if we have any more. I think we answered all the questions. All right, awesome. I just want to say thank you all so much for attending, and thank you so much, Arya. Your presentation was very informative. I enjoyed listening to it as well. And thank you all for attending again. The webinar will be available on the Viscosity channel, which is our YouTube channel, as well as everyone who was present today will receive a recording of it once that's uploaded. And without any other, there are no other questions, I will conclude the webinar for today. Thank you again, everyone, and I hope you have a nice rest of your day and a nice rest of your week.
So, see you guys.